this. So this model along with the properties that I have. So let us start. First, so we'll work in mm, not in meter. Continue it. And then what is the dimension? 210 by 130. 210 by 130. By 130. So our beam is ready. Beam length is 3 meter. Then we need reinforcement bottom 10 mm. We'll use wire planar. Now for length of reinforcement we need to get the side cover. So can you tell me what is the side cover? 20 mm cover to reinforcement. All dimensions 20 mm cover to reinforcement. Bond, can you tell me what is the cover? Side cover? Okay, we'll take 20 mm only for side as well. So the length of the reinforcement would be 3000 minus 40. So it will be 3000 minus 40, that means 2960. So another one, same length, just 6 mm. So I've made 2 reinforcement bar. Then I need to make stirrups. It will be also wire. And as there is 20 mm cover, so the 20 mm cover to reinforcement. Okay. Then this will be 210 minus 40. It will be 170, right? 170 by 170 by 90. And if this is a clear cover or effective cover, they have not mentioned. So if I am considering the clear cover, then in that case, if this is the reinforcement and if cover is from face, and I am making center line diagram, so diameter of reinforcement is diameter of stirrups is 6 mm. So what I'll do is so the diameter is 6 mm. 20 plus 6. Okay, let it be effective. So this is 90 and this is 170. 90 and 170. So first I'll bring the bottom bar along with the stirrups. Now I need to rotate the bar. I'll rotate this one. I'll rotate about y-axis. So first point was 0 0 0. Next point any value in y-axis 0. Rotate it 90 degree. Now yes. Now this okay. Now the diameter of reinforcement is 6 mm. Sorry, stirrups is 6 mm and diameter of bottom bar is 10 mm. So first I'll hide this beam and I'll create a point from this point x direction. So it will be 3 mm plus center of this bar will be at a 5 first not 8 mm. So minus 8 mm x minus 8 mm sorry plus 8 mm y and z will be 0. This point I'll bring the center of the bar at this point and there are 3 bars. Does they have given the spacing? No problem. Similarly again I'll create a point 8, y will be 8, z will be 0. I just need 2 more bar, so I'll pattern it. So I've created 2 more bars. Now one of this I'll place exactly at this point and other one I'll create a midpoint between these two. And then I'll translate this bar, this point to here. Now just let me check top bar. Top bar is of 6 mm dia. So offset from this point will be for top bar 3 mm for stirrups and 3 mm for main bar. So it will be 6 mm minus 6x and y will be minus 6, z will be 0. Similarly from this point also let me create 6x, y will be minus 6, z will be 0. I'll bring the smaller diameter bar and then rotate it. I'll rotate about y-axis. What happened? Somebody have left. Okay. So it's done. insert this bar. Here. Next, I'll pattern this bar because I need two more bars, sorry, one more bar. So I'll simply create only one more bar, and I'll place this bar here to here. Now there is a gap between stirrups and bar, if you see clearly, that is there, but once we assign the section, this gap will not be there. Now let me make the model 135 mm stirrups, spacing. So pattern this one, I'll choose this direction, I'll reduce this. This is 135 mm. Keep on increasing until it reaches the end point. Okay, so I guess bars on either side. and 35. I'll give the number 11. So if I increase one more bar on this side, now what I'll do, I'll get the midpoint of the stirrups, only for stirrups. So midpoint of the stirrup is this. This one is the midpoint of the stirrups, and for reinforcement bar, this will be the midpoint, because I have already placed at the mid. So what I'll do, I'll simply select all the reinforcement bars and I'll coincide their centered. So if you see, on either side we have minimum spacing. So total, I guess 12 plus 11, 23 bars, 23 stirrups. So our stirrup is ready. Now first of all, I'll make the constraint. I'll go to interaction and I'll use embedded constant. Select this one. You can select whole model. So now I'll use the embedded constraint. I'll select whole model.
So you have a share screen.
Okay. Embedded constraint have been created. Now I'll switch off everything. I'll simply switch on the beam, because now I need just to place the reinforcement inside the beam. So as I have considered 20 mm cover from either side, or alternatively what I can do is I can simply create a center point for this beam also. So this is the point and this is the point. So I've got the center point for the beam. This is my center point for the beam. Make sure you do not make any mistake in selecting the center point. This is the center point. So I'll simply drag this center point. I drag the beam using this center point to the center point of the stirrup. I'll switch on everything, and if you see properly, this is the center point. For the stirrups. See, there are so many points, so I'm getting confused. What I'll do is I'll delete all the previous points, so I can go for assembly and feature and delete all the data points that you have. So it will clear all the data point or simply suppress it. Now I was getting confused. I could not recognize which one was center point. Now I'll again switch off everything. I'll switch on only the beam, and I'll create the center point for the beam. And I'll switch on everything. I'll switch off the beam. And I need to get the center point. So this is the point I've got. Now I'll switch on the beam. I'll drag the beam using this point to that point. Now if you see the front view of the beam and give a transparent look, so you can view the reinforcement. Click OK. Now see, the reinforcement has been placed exactly at the center. You check at the side view or top view. Okay. You can delete all the points. Now let us get the support point, at which point it has been set. From either end at a distance of 2700, means at a distance of 150. From either end at a distance of 150, the supports have been placed. Now I can simply create a support. Extrusion. I'll use a circular part. I'll give a random diameter because here they have used a random diameter. Let us skip 50. And it is 130. If I bring it over here with an auto offset, the support has become too big, so I'll simply reduce its dimension, and also I'll edit it and I'll make it discrete rigid. So I'll reduce the dimension and make it 25. Feature, regenerate, assembly. Okay, this is okay. I'll assign a reference point. Go to assembly. Now from this point x is 0, y will be 0, z will be 150, minus 150. Just I need to put a support, and I don't know why there is so much network issue. Okay, so now for the top loading point, it is 1000 mm from a support. That means it will be 150 plus 1000, 1150 from one end. So this point, x is 0, y is 0, z will be minus 1150. Okay, now I'll have to first rotate it. Then rotate about y-axis. Press enter. 90-degree rotation. Done. Now it has got inserted somewhere inside. I have to bring it outside. Now see, I need to place it at the bottom, so the top point of this cylinder should be at the bottom of the beam. So I need to create a top point, and I'm not getting any point at the top. So what I'll do, I'll simply partition it so that I can get a point at the top. So partition of shell using partition of face using okay, I'll use a datum plate. For that I'll create a datum plate using 3 points, first, second and third point, and partition this face using datum plane. It is asking me to select a datum plane. I'll select this datum plane. Partition created. Again I'll create datum plane, vertical datum plane, 3 points, 2 points on one plane and 1 point on the other plane. Now again I'll partition it using datum plane. It is asking me which face you want to partition. I want to partition whole face, and using the datum plane, this one, create partition. So we're good to go. Now if I bring it in the assembly, see, I've got a point. Now if I try to push translate it, then I'm getting a top point. I select this and I select over here. Now if you see the front view or side view outside, it has been placed exactly at the bottom. Good. Now I'll make a copy of this. At a distance of, supports are at a distance of 2700, and vertical one, what is the 25 and 130, 135, 145. 25, 145 plus one more 25, it will be 70. So not good. I just want two more. Okay, sorry, it was 210. So 210 plus 50, 260. Okay, 260 exactly at the top, but we have to place it at a proper location. Now we placed it but not properly. So from this point, from this support, the distance of the first loading point is 1 meter. So it is 1000. It is just flip the direction. Perfect. And again I need another copy of this in the same direction, but 1000. I don't need this. So loading point have been defined. These two are extra, so I'll delete these two. I'll delete this one and I'll delete this one also. Now for this simulation I'll go for static analysis. It will take some time for the simulation to complete. Now bond, set up these values like this. Set up these values, keep it 0. Go to increment and follow all these values. Because now in load, as I don't need all this, so I'll simply, for the time being, I don't need strain, etc. I don't need contact, etc. But what I'll do is I'll replace the damage pattern. here I'll go for space-time interval and I'll ask for 20 outputs, or I ask for 30 outputs, that's okay. And load, here we just have to follow the boundary condition what they have used. So elastomeric pad steel plate, or simply supported.
So I haven't gone through properly the papers.
I should have, no problem. For the time being I'll keep it a roller for both ends. But this, so we have the support on which these beams are resting, so I'll fix the support, and on this support the beams are simply resting. And for load, this is my reference point for load. And then load in U2 direction, and to apply a displacement of -30. In U2 direction a displacement of -30. I just have to go to mesh before applying any property. So the part, use the default mesh and see, no, this is not good. I'll use 5 mesh size. This is quite good. For beam, if I use default mesh size, it will be too high. 50. Okay. Reinforcement, go for 50 only, and change this reinforcement type to truss. Mesh cells. Change the reinforcement type to truss. Stirrups, it was 17, I'll keep it in. Change the mesh type to truss. Save the model. And one more thing, I just have to find out the set. For the set 2 is my support and set 3 is my loading. So I'll go to set 2 is my support. So I'll request history output. Set 2 is my support. So in support I'll only get reaction force. So RF2, and I'll copy this. Here I'll change the set to set 3. Here I'll get reaction force as well as the displacement. So we'll be able to plot load versus displacement curve. So this model is completed in every way except for property. So for property, let us create a material concrete, density 2500, e to the power -12 ton per mm cube, elastic. So whatever I have in the Excel file, I'll enter that data directly. Then go to plasticity, concrete damage plasticity, enter this data. Compressive behavior, we'll go for the bottom also. tensile behavior. Tension damage. Click OK. So all the data have been defined. Click OK. Steel density is given -12. Elasticity and plasticity. For that, I guess we have saved something. Yeah. For 6 bar, you have a different value. So I'll rename this again. I'll click OK. Okay. I'll enter it for 6 393.6. 393.6. Plastic strain 0. I'll give a ultimate strain letter, ultimate stress of, let's say, 415 or 600 at 0.18 strain. Modulus of elasticity 208.4 and 4 to the power 3. Poisson's ratio will be 0.3. So this is steel 6 mm and I will copy the same material and name it 10 mm. What I have to do over here, I just have to change the elastic value, which is 199.2 to the power 3 to the power 3. Plastic 540.8 and let us give it ultimate strain of 800 and 0.3 strain. So we have defined all the property. Just we have to create the sections. So 10 mm bar, beam, truss. So to select for 10 mm bar. For 10 mm bar, cross section will be 78.54. 0.7854 d square, 5/4 d square. And for 6 mm bar, just find out the area for 6 mm bar. Bar, the area will be 756 into 36, 28.27. Simply assign, this will be 6 mm, this will be 10 mm. Again 6 mm. So we are done with everything. I just have to define our interaction. So I'll switch off everything. Or let it be, everything be there. And simply use this one. Find contact pair. It will automatically give you the contact pair. Go to property, create a property. Give tangential behavior penalty a value of 0.1 and normal behavior hard contact Your model is ready. I'll simply submit the job. I have 4 processors, so I'll use all the 4. So faster. Submit the job. Okay, sorry. I have forgotten to assign the property for the beam. So I'll assign the property. I'll create the it will be solid homogeneous. Okay. Click OK. So everything is done. Just submit the job and you will get your result. Hello. Okay, the analysis is completed. The analysis is completed. I will simply right click and click on result. So this is the tension crack pattern we have got. To see the bottom tension crack pattern. This is the bottom. From here you can get tension, damage T, damage T. So compression damage and tension damage. So this is the tension damage. If you want to plot load versus displacement curve, simply expand these two and plot the first and this. Right click, plot. So once you plot this, the data load versus displacement curve will be available here. So right click and save both of this. XY data 1 is my force. So this is force. This is displacement. Sorry. This is force and this is time. So this not required. Take this data in Excel. Force column. And this one is displacement. So right click and simply take this data in Excel. Plot the load versus displacement curve. Convert the minus displacement